So I said in the beginning that the equation of radiative transfer, we're hiding all of the complicated physics inside of the source function. Let's unveil that complicated physics. Let's look at what is inside the source function, and that comes from the Einstein coefficients. Let's consider the energy absorbed. The absorption law states that the energy removed from the beam is the opacity times the density times the intensity. In terms of microphysics, the energy that is removed is the number of absorption events times the energy of each photon. The number of absorption events is nb times I, n1b12 times I. And the energy of a photon is h nu. Now, similarly, the energy that is emitted is the number of emissions times the energy of each photon emitted. And the number of emissions is the right-hand side of the equation, times the energy of the photon. You have an intensity in this term that is not showing up in the emission law. So we can pass this term into the absorption, treating it as negative absorption, as you saw before. And then you have an effective absorption and an effective emission. So we can cross the intensity from the absorption. And now you can write the source function by dividing the emissivity over the absorption. Now, dividing one by the other, you cut the h nu and the rows. Now we can extract the n1b12 from the denominator. And then we can use the second Einstein relation to eliminate the b21. The second Einstein relation was that b21 is equal to g1 over g2 times b12. So we substitute this expression for b21. Now, this is the most general form of the source function for this simple system of two energy levels. You can see that when you have thermal radiation, the levels then obey Boltzmann law. You have N1 equal to N2. And substituting these energy levels, then the source function becomes the Planckian.